We're here. Yes?
Yeah, I think it becomes easy. So let's say that I'm thinking that I'm going to try it, so I think it's going to go to you.
Yes, yes. Okay, so look, the exam 3 is a week from today. We are going to do curve sketching today, probably a little more curve sketching Thursday. We'll just have to see. I might squeeze mean value theorem in there. It's not, mean value theorem is not a big section. It's just it's a formula. That's all it is. So we'll see how things go. But the test is on Tuesday. The test will consist primarily of derivatives of exponential and log functions, logarithmic differentiation, which is, we used logs to take derivatives. Do y'all remember there was a problem over there on the board and you used the log and it made it a lot easier?
Or we could apply the property of logs.
Exactly. That's going to be on the test. L'Hopital's rule, which is a big section, okay? In L'Hopital's rule, remember there's also logs. That's how we dealt with some of the indeterminate forms. And we're going to talk more about this on Thursday, but I'm just kind of giving you a heads up. And then you're going to have to be able to find the absolute max and min of functions on a closed interval, which is 4.1. We skip 4.2. You'll have part of 4.3 on the exam, which is figuring out where a function is going up, where it's going down, concave up, concave down, inflection points, local max, local min, but you won't be asked to do a full-blown sketch. All right? That's what this is. This is the take-home portion of the exam. I'm thinking this will be 20 to 30% of the total grade. These 4 problems are to be done in detail following the methods that I'm going to show you here today. All right? So, pardon me?
It shows the rest of the methods.
Rest of the methods?
Because you said there was more, right?
Yeah, that's what I'm going to do today. Yep. So the instructions here, I do want you to work alone. I don't want you to all meet up at Starbucks and knock this thing out. I will consider that to be academic dishonesty. So don't go take this to the tutoring lab and ask them to help you. If you need help, I say come to me only. That's me inviting you to ask questions. So if you do get to a point where you think you've done something correct and you just want to run it by me, I'm willing to take a look at it. One of the best things for you to do would be to just take a picture with your phone and send it to me as a text using my cell phone number, which is on the syllabus. Just make sure if you do that, let me know who you are, what class you're in, all right? And make sure your picture's good before you send it. Huh?
How will you help us?
Well, if you have a question, you can ask. I mean, the most I can say is I can't help you with that, or I can refer you back to the notes, or just make sure you ask good questions. Sometimes I'll get questions. This happens a lot with my internet students. I'll get a question on how to do something, and I'll reply to their question with a link to, you know how in YouTube you can link the video to the exact time in the video? And I'll link them to the exact second where I tell them what they're asking me. That always makes them look bad. It makes them look like they haven't done enough of their own work, you know? So do your own research, look at our lectures, look at the homework solutions before you ask something that I'm going to be able to answer with a video. You understand? But please do ask questions. Worst that's going to happen is I'm going to say I can't help you with that. Just well thought out questions. Questions that make me believe that you've put in the time.
Like, not what's the answer to number 4, right? Just kidding.
Yeah.
Is this in the correct direction?
Yeah, you just ask. I mean, it's better than not asking. So there are 4 questions here, 4 problems to graph. The first one being basically you're just going to show me you know how to do this. Easy function, easy derivatives. Everything's pretty clean. And then they get a little, a little messier. And the last one is a function on a closed interval, which is somewhat interesting.
You should be happy though.
Well, I don't know if you should be happy because you're asked to sketch it. You're not asked to find the absolute max and min. If you're just asked to find the absolute max and min, you would be real happy because then you could use a closed interval method. But it's not, the instructions are to graph. All right? So what I'll do today is I'm going to try and do two problems today. We'll see if I can get through them. And if I can, that's a good thing. In my other class, my Monday, Wednesday class, I did 2 problems yesterday on video. Those problems that I did, I would recommend you go look at. Do you all know how to get to my Monday, Wednesday class videos?
I think so.
You can figure it out? Okay, if you can't find it, send me an email. But
On the YouTube.
it's on YouTube. I think it's day 20.
Literally says MW and then it says TR.
Yeah, it says MW for Monday, Wednesday, TR for Tuesday, Thursday. So I did 2 complete curve sketching problems in their class yesterday. I told them to watch the video of your class today, because I'm going to do 2 different ones today. So theoretically, you should have 4 examples of completely worked out curve sketching problems.
Which is what you want.
Well, not these 4. I'm not going to do
Well,
these. Yeah,
what you want on this.
yes. So, but I am not doing homework solution videos for this section.
Why not?
They're just too long.
Yeah, homework
They're too
videos,
long.
3 videos.
So I've opted out of that. Sorry. Maybe if I have some free time, but I've been pretty busy lately with a lot of different things going on here on campus. So, so what am I going to do today? Why don't we start with number 16. I feel like I did 16. Hold on, I did 16. How about 14? This is 4.4. We're doing 4.4. Oh, and I should tell you what we're going to do. All right, so for 4.4, what we're going to do is everything that we did last class. Figure out where the function is going up and down, where it's concave up, concave down. All of that information we're still going to do, but we're going to add some more things to it that includes some analysis that we did in college algebra, and then some other things that we did involving limits. So let's just walk through each of the steps here. First thing you want to do is find the domain of the function. That's a college algebra problem. What can you plug in? What can you not plug into the function? Find the x and y intercepts. You remember how to find x-intercepts of a function? Set the function to 0. How to find the y-intercepts? Plug in 0 for x and figure out what the value of the function is. So that should be pretty clean. This step 2 should be pretty clean. Check for symmetry. Now when it comes to symmetry, I'm going to put an asterisk next to this. I'm not going to require this step, all right? But if you do it, I will consider that bonus. All right, symmetry is where you're really checking to see if a function is even or odd. So do you remember from pre-cal that the cosine function, cosine x, was an even function? And what that meant is when you graph cosine, that's cosine, that if you reflect it over the y-axis, it's the same thing, right? Like a reflection. That's what it looks like. That's an even function. Here we would say it's symmetric to the y-axis. So if you look at a function and you determine it's even, then you know that it's a reflection over the y-axis. Now what does it mean for a function to be even? Well, that's why it's bonus. You'll have to go back and look this up from college algebra. But this is what it means for a function to be even. It means when you plug in x, it's the same as, you get the same thing as when you plug in negative x. They give you the same value. That's one type of symmetry. The other type of symmetry, a quadratic, exactly. Quadratic, that's thus the name even, is because even powers are all symmetric to the y-axis. Even powers of x.
So this could only theoretically happen in quadratic and logarithmic functions?
No, because not every function that's an even function has to be a power function. Like cosine is even,
Or absolute barrel.
right?
Absolute
absolute value, but I don't know, what was your question? I thought you were saying to be symmetric on the y, it has to be an even power.
Like a quadratic and logarithmics or whatever.
Logs wouldn't be symmetric.
I forget the name for cosine. Trigonometry?
Trigonometric?
Yes.
Some trig functions are even, some are odd. So you have to look at them. This is what it means to be even. You plug in x, same as plugging in negative x. If we look at the example, f of x is x squared, then if I replace this x with a negative x, I'm still going to square it, right? So it's still going to be x squared. So these two are the same. So since they're the same, it's an even function. Now if we take a function like sine x, if we graph sine, it looks like this. If we reflect that over the x-axis, the y-axis, that's not sine, right? Sine would actually come this way, like that. So this is not an even function. But imagine reflecting this over the y-axis first. It would look like this, right? That's what sine would look like reflected over the y. Reflect it, and then take that and reflect it over the x. And wouldn't it lay right on top of it? That's called an odd function. Now, again, I'm not going to get into this in detail because of time, but we can check for symmetry to help us graph. We can say, oh, look, when we draw it at the end, we know that it should look like a reflection. Like that, it would just be knowledge that we could put into our data bank of all this information. It would help us graph. All right, finding asymptotes. There are two types of asymptotes that we deal with, vertical and horizontal. So when do we get vertical asymptotes? I'm going to put VA for vertical asymptotes. Vertical asymptotes occur anytime in your function where you have fixed over 0. Where you have division by 0, but the top is not 0. And you might remember this when we were doing limits. When we did a limit and we saw this, what were the possible answers? Fixed over 0. Infinity or negative infinity. Which meant the function was either going, what, up to infinity or down to negative infinity? And if you go back in college algebra and take a look at functions, or even pre-cal, we had some functions that did like this, right? Maybe like that. And that would be a vertical asymptote. As we approach this, it goes up forever or down forever. That happens when we get division by 0, fixed over 0. Okay? That's how we're going to identify vertical asymptotes. The other types of asymptotes are horizontal asymptotes. And again, from college algebra, those are the ones that come out the sides like this. And those are where our function kind of flattens out towards those. Those look familiar to you? So if you look at this picture, the horizontal asymptote is telling you where your function goes as you go out to the left, right? And where your function goes as you go out to the right. Another way of saying these two things is this. You could say for this, to figure out what's happening, you could take the limit as x goes to infinity of the function. Isn't that the same thing as me asking you where does the function go as you go out to the right forever? Yeah? So to find horizontal asymptotes, I should probably tell you this. Horizontal asymptotes, what you're going to be doing is taking a limit. You're going to let x go to infinity on the function and see what happens. But you also have to do it over here. Limit, this time x goes to what? Negative infinity of the function. So you'll do both. Understand? Find the verticals by looking at where you have division by 0. That'll help you draw your graph, right? You'll have vertical dotted lines. Or you may not have any. It just depends on the problem. Horizontal asymptotes you'll get by just taking two limits. And that'll help you determine if your function flattens out or not. Not all functions flatten out. They might not. Do y'all understand these are all just graphing aids just to help us get an idea what the picture looks like? Was there a question?
I was trying to remember what we did in algebra algebra to find those?
Well, in algebra, we restricted ourselves to just rational functions. So we compared the degree of the numerator and denominators. But here in calculus, we're not guaranteed rational functions. So what we'll do is we'll let x go to infinity and see what happens. And most likely we're going to get infinity over infinity, and then we're going to use L'Hopital's rule. All right, and then after step 4, everything else is pretty much the same. Step 5, where is it going up and down? Yes?
Can we expect oblique asymptotes?
I will not ask you for those. The oblique ones, the slant asymptotes, you don't have to get those. And then, do you see 5, 6, 7, 8, 9 are all what we did last time? Do you remember the Bobby method? Did we talk about the Bobby method? Right? Yes? Bobby method? Okay, so this is pretty much the table is Bobby method. And then sketching. It's just when we get to this sketching piece, we're going to put all this information together. We're going to put our x-intercepts on there, our y-intercepts on there. We're going to put any asymptotes we have. Everything's going to be there. It's going to help us have get a really good picture of what this function does. You ready? Let's do one. Or let's do 2. All right, y equals x squared over x squared plus 9. I'm going to try and move kind of quick. All right, so please let me know if I'm moving too fast. Stop me, ask for clarification. First step is to find the domain. So all real numbers? That's because you're never going to get division by 0, right? X squared plus 9, that can never be 0 because, why? Why can't that be 0? X squared can't be negative, right? And the only way to make this 0 is if that was a negative 9. So there's no way that x squared could be a negative 9. So you're never going to have division by 0. That means you can plug any number you want into this, right? All right, next step, x-intercepts, y-intercepts. So let's do x-intercepts. To do x-intercepts, I set the function equal to 0. And let's call this f of x, everyone. I want to use f throughout this. Can we call this f of x? All right. So set the function equal to 0. So you have to set that entire fraction equal to 0? Just the top, right? Because again, back to what we learned, anytime you have a fraction equal to 0, you just look at the numerator. So this means x squared must be 0, which means x is 0. That is an x-intercept, right? Now let's find the y-intercept. To find the y-intercept, we evaluate the function at 0. We plug 0 into the function. And it just turns out in this problem that we get 0, don't we? Now, I wouldn't expect you to start drawing a picture right now, but I just want to show you what we have so far. I know that this function, when I draw it, is going to be everywhere, because it's defined everywhere. And I know that at the origin, I have a point. That's both my x and y-intercept. Just so happens in this problem, it's the same point. That's what I have so far. Now I continue. Third step, symmetry. I'm just going to put sim. For symmetry, my gut is telling me that this is even, only because I'm seeing even powers. So let me try it. Is it even? This is a question I'm asking, right? Is it even? Well, what I need for it to be even is for f of x to be equal to f of negative x. Is it? It is. Because f of x is just x squared over x squared plus 9. And if I put negative in there for x, these two would be equal still, right? Because when you square the negative, it's still going to be positive. When you square the negative, it's going to be positive. So it'll be identical to that, won't it? So this is an even function. And therefore, I have symmetry. Again, I don't know what it looks like, okay? Whatever it looks like, it's going to look like the same. It's going to look like the same thing on the other side. It's going to be symmetric over the y-axis. So this is a little arrow curling. You see that? Y-axis symmetry. By the way, how do you check if something's odd? Do you know what needs to be true? Like this is what you need for even. Do you know what you need for odd? You need f of negative x to be equal to negative f of x. That's what you need. You need to get whatever you, when you plug in a negative for x, it needs to be equal to not the function itself, but the whole function change negative. That's what makes a function odd. And this is called symmetry. By the way, this right here is called symmetry over, pardon? The origin, good. Even functions are symmetric over the y-axis. Odd functions are symmetric over the origin. All right, so I just got bonus points for doing that. 4. Step 4 is what? Asymptotes. All right, so let's take a look at the asymptotes. For 4, let's look at vertical asymptotes first. Do you ever get fixed over 0? Nope. Never going to happen. Right? So there's none. Now, just for the sake of demonstration, what if that was x squared minus 9? You'd have 2, right? You'd have 1 at 3 and at negative 3. But that's not the function. I'm just saying that's what we would have identified. All right, for horizontal asymptotes, I said you had to do 2 limits, right? Limit as x goes to infinity of x squared over x squared plus 9. And then the other one is the limit as x goes to infinity, negative infinity, of x squared over x squared plus 9. I have a feeling I didn't start my video. Oh, I did. I don't remember starting that. Right, 2 different limits. This first limit is going to tell me where my function heads as I go out the right side. The second one is going to tell me where my function heads as I go out the left side. So when I take this first limit on top, what do I get? Infinity over infinity. So I'm going to do L'Hopital. Everyone agree? Infinity over infinity? Yeah. Okay, so I use L'Hopital real quick. And derivative of the top is 2x. Derivative of the bottom is 2x. And that's just 1, isn't it? Yep. You do not do infinity over infinity again. Remember? You don't do that. If they simplify algebraically, then you do that. This is just 1. And now as x goes to infinity, x isn't even here anymore, right? So this is just 1. And then what about the bottom? Same exact thing. It's going to be 1 also. And the only reason it's 1 is because when you square the negative, it's going to be the exact same thing, right? You're going to still have positive infinity over positive infinity. And you'll do L'Hopital on it. You'll get 2x over 2x, and then it will turn into a 1. So that means out the right side, it's headed towards 1. Out the left side, it's headed towards 1. Make sense? So again, if I was drawing, which I'm not, this is just a mental picture I have in my mind right now. I know I have this, right? I know the picture exists everywhere. And I know as I come out this way, I'm going to be up 1, right? And as I go out this way, it's up 1. And be careful, never draw your horizontal all the way through. Hopefully that was stressed to you in college algebra. Don't draw your horizontal asymptote all the way through. Horizontal asymptotes only give you end behavior, left end behavior, right end behavior. It tells you nothing about the middle. If you draw it all the way across, you might think you can't cross it. You might accidentally think that you have a barrier that you can't cross, and that's not the case. All right, so that's my mental picture of what I have so far. What's that? I didn't hear you. All right, step 5. Where's the function going up and down, right? All right, so critical numbers, so we've got to take derivatives now. So let's take our first derivative. Quotient rule. I'm trusting you could all take the derivative of that pretty easily. Right? Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. I'm curious, just a show of hands, and I won't hold this against you. Does anybody do the book's formula here instead of the formula that I provided? Anyone? No? Everyone does derivative of top times the bottom? Minus? Okay. All right, let's clean that up. Distribute through. Multiply those together, so we should get 2x cubed plus 18x minus 2x cubed again. Oh, that's going to be nice. Two x cubes cancel. And I get a pretty clean version of the first derivative, don't I? So to find the critical numbers, I need to do two things to that. Figure out where it's 0, figure out where it's undefined. So let's start with it being 0. Where is this derivative 0? You said 18x equal to 0, right? Just the top? Just the top to 0. And that's just 0. What about where it's undefined? It's defined everywhere. You can say undefined or does not exist. It doesn't really matter here. Because you can never make the bottom 0. For the same reason we couldn't make the bottom 0 here, right? So, nope. No go. Now what?
Second derivative.
We could do second derivative, but this is where we did the number line and we did all that stuff, right? So let's go ahead and do that. Number line, what goes on this number line?
Critical numbers.
Critical numbers, which I only have one of them, right, at 0. I like to box that. That splits me up into 2.
So negative 1, 1.
Is anyone going to be bothered if I take my shoes off? I don't know why, just these shoes are really bothering me right now.
Are they new?
No. Okay. All right. Everyone's going to pass out up here.
We get extra points for that.
I get extra points. See how many students I can knock out. Okay, so I've split the number line in 2, right? Why did I box the 0? It's a critical number, but there's another reason I boxed it. And that's because this number lives in my domain. All right? I want to make sure that I'm clear that this number is something that if I get up then down here, it's going to be a local max. If I go down then up, it's going to be a local min. There are times when you'll have a number here that's critical, but like let's just say I had 3 here. Say that was a minus in here, then that number 3 could not be plugged in, right? But it would still be a critical number because it would cause, it's an important point on the graph. It's a vertical asymptote. And so I would want it here. I would still want to split my number line up and see what's happening to the left and the right of it. But if I got down and up here, this would not be a minimum because 3 is not in the domain of the function. So what I do is I box anything that's in the domain, anything that's not in the domain, I would leave it unboxed. Maybe if we do another example, you'll see that. If you watch the video of the class I did yesterday, that happens. So in the example I did yesterday, one of them, I had that issue. All right, test points, right? Something to the left, something to the right. So -1 and 1. And these, I like to circle. These go into the derivative, right? Because it's going to be telling me if it's up or down. All I care about is positive or negative here, right? So I think I can do it. I think I can do it visually. What can you tell me about the denominator? No matter what I plug in for x, that's positive, isn't it? Positive on the bottom, no matter what. So let's try this. -1 up here. 18 times -1 is -18. -18 over a positive number is still negative. So this means that my original function is going down over here. So it's looking like, if anything, I have a local minimum. If anything.
And then it's going to go up on
It's going to go up on the other side. If you plug in 1, you're going to get a positive 18 on top, and it'll still be positive on the bottom. Any questions? All right, let me summarize this like we did before in the work from last week. Where is f going up? 0 to infinity. Where is f going down? Negative infinity to 0. Good. And do we have a local max? No. None. Local min? Yes. Where is it happening? 0. And then now I'm going to actually figure out the point on the graph. So I'm going to take 0, I'm going to plug it into the original function, and we already knew that was an x-intercept, didn't we? 0, 0. All right, so that little point 0, 0 is an x-intercept. All right, that's good. Now, that was step 5 and 6, I believe. This was part 6. No, I think 6 was this part, right? Getting this? Local max and min? When I say step 6, I'm referring to this. Find all local max and min values. Where do they occur? Now I'm on to 7. Determine intervals where it's concave up, concave down, all that goodness. 5 and 6 are done in kind of in one shot here. So for part 7, I'm going to take the derivative of the derivative to get my second derivative. So I've got another quotient rule on that, right? Derivative of the top, 18, times the bottom, which is x squared plus 9, that quantity squared, minus, now the derivative of the bottom. What are you going to need to take the derivative of the bottom? Chain rule. Right? Because this is this thing squared. So derivative of that thing squared would be 2, right? X squared plus 9 to the first power. Then go inside, take derivative of what's in here, which is 2x. And then, don't forget, times the top, right? 18x. That's your beginning of the quotient rule. Now you have to go divided by.
Could you just leave it like that? Like right before it says.
Like that? Yes, that's what I'm doing. So it becomes the fourth power. And we get to clean that up now. Now, before you start cleaning this up, your instinct might be telling you, okay, I'm going to take this and I'm going to square. So I'm going to expand it out, and then I'm going to distribute an 18 through it, and then I'm going to figure out what this is with the 2 and then pass that through. That might be your instinct. But instead, what you should do on a problem like this is try and see if you can find a GCF in that numerator. So look at, you've got kind of two pieces. You've got this whole thing and this whole thing. What do those two things have in common? There's an 18 in both of them and an x squared plus 9 in both. Right? This has an 18, that has an 18. This has an x squared plus 9 squared, this has an x squared plus 9 to the first, so I can pull one of those factors out. So here's what this is going to look like. The 18 came out, the x squared plus 9 comes out, and then I'll put a bracket here. I could use parentheses, but I'm just using bracket. What would still be here after we pull this out?
X squared plus 9.
X squared plus 9.
Plus 2x plus x.
And then out of here, I pulled this out, right? This came out, and this 18. So I'm going to kind of scratch them out so I don't use them. So what's still there?
Minus 2,
2 times x, so minus 4x squared?
Yeah.
What? 2 times 2 times x, so minus, because it's a minus, 4x squared. And that's all over x squared plus 9 to the fourth. And we can clean up the bracket, right? inside the bracket will become 9 minus 3x squared. And then what about, there's something else I can do algebraically. Do you all see it?
You cross out one of the x
I
plus 9.
cancel out one factor of the x squared plus 9 with one of these factors. That would leave me a 3 there. So this would give me, let's see, 18. And then that bracket, I'm going to use a parenthesis instead of a bracket. And then over x squared plus 9 cubed. And that is a pretty good looking second derivative. Right? Would you agree that's pretty cleaned up? You know what? I could pull a 3 out, couldn't I? I could pull a 3 out of this. If I wanted to, I could. I could leave it also. I'll just leave it. All right, so there's my second derivative. I need to figure out where it's 0, where it's undefined. So let's talk about it. Where is my second derivative 0? So I'm going to set the numerator equal to 0. I can divide by 18, right? It's gone. If I divide by 18, I've got 9 minus 3x squared equals 0. I can move the 3x squared to the other side, make it positive, divide by 3, and square root. So plus or minus root 3? Two critical numbers. In my college algebra class, I always tell them when we take the square root on both sides, I always tell them if you initiate the square root yourself, you always have to do plus or minus. And if you forget that, it's a big deal. And a lot of times they're like, well, why is it such a big deal? I'm just missing one of them. Do you realize we would be missing an entire critical number? Which means on our number line, we'd be missing an entire region where we'd be testing for concavity. That's going to have a major impact on our picture. And in the bigger scheme of things, engineers and stuff, people die, planes fall out of the sky. When people forget the square plus or minus. I used another analogy in my college algebra class last semester, and they all got shocked. I was like, bridges fall, planes fall out of the sky, bus loads of children go off the edge of cliffs. So they're like, what? I think I went over the edge a little bit, but they remembered it.
We should try to make puns too.
I think the same for the rest of that class was, well, your bridge collapsed.
Yeah. All right, am I done looking at the second derivative?
No.
I need to figure out where it's undefined. And it is defined everywhere because I've got that same x squared plus 9 in the denominator, which is never causing a problem. All right, number line. Were there any questions on where I got the negative root 3, positive root 3? No, we're good? This creates 3 sections. I am going to box these because they are in my domain. Test points. Something over here, something over here, something over here. Negative 2 would work. 0 and 2. And these are getting plugged into second derivative, which I've conveniently erased. But I see part of it. It was 18 and then 9 minus 3x squared over. What can you tell me about the denominator? It's that thing cubed, right? But the x squared plus 9 that was being cubed, that x squared plus 9 is always positive. And you cube a positive number, the bottom's positive. So I'm just going to say, hey, look, the bottom's positive, right? All right, let's try negative 2. Negative 2 squared. 4, right? 9 minus 3 times 4. That's 9 minus 12. It's a negative number. It's going down. No. Oh, whoa. Hold on. It's frowning. Okay. Concave down. I know what you meant, but I drew the wrong thing. 0 gets plugged in for x, and that's gone. So 18 times 9, that's going to be positive, so concave up. And we plug in 2. That would be the exact same thing as plugging in negative 2 because we're squaring it. So concave down again. Bam. I'm going to do my table. Let me summarize. F is concave up on negative root 3 to root 3. F is concave down on negative infinity to negative root 3 union root 3 to infinity. We've done this before, right? You feel comfortable with that? Any questions? Inflection points. Do we have inflection points? Yep, we actually have 2. Remember, inflection points occur when you have a change in concavity. So if you go from concave down to concave up, or concave up to concave down, these are inflection points. So long as these points are in the domain of the original function, which they are. So I'm good to go. So I know one inflection point is negative root 3 something, and the other one is positive root 3 something. So where am I going to plug those in? Original function, right? So what happens if I take negative root 3 and square it? I just get 3, right? The negative will go away because negative times negative will be positive. So that's just going to be 3. And then down here, same thing. 3 plus 9, 12. So 3/12 is 1/4. Yes? Okay. And then what about if I plug in the positive? Same thing. Hey, you know another way you could determine that this would be the same thing? Because it's an even function, right? It's an even function. So when even function means that whatever you plug in, if you just change the sign of this, it has no impact on the answer. It's the same answer. That's what we meant when we said f of x was equal to f of negative x, right? That means plug in a number, then plug it in, but change it to negative, you should get the same answer. So plug it in negative, change the signs, you get the same answer. All right, we are in business. Time to draw. So this is where we make the table. This would be step, I don't even know. Is it 8? Yeah. No?
Yeah,
8? Okay, 8. So I'm going to make my table. And what numbers go on this table? Critical numbers, both from the first and second derivative, right? And I make enough room for 3 rows. F prime, F double prime, and F. All right, what were my critical numbers? I think it was just 0, right, on the first derivative? 0 here. And then root 3 and negative root 3 I got for my second derivative. From what I can remember, we had a local minimum, didn't we? At 0? Local minimum? Was it minimum?
Yeah.
Yes, it was. So it went down, and then up and up. So to the left of 0, it's going down. To the right of 0, it's going up. And then when it comes to my concavity, it was concave down to the left of root 3, concave up between negative root 3 and positive root 3, and then concave down again after. Am I moving too fast, or is this making sense? You'll need to let me know if you're getting rolled over here. Right? Yes?
So to get the 1/4 of the inflection, which function do you use?
The original. Because we're trying to pull, just think of it this way. An inflection point is a point on the graph. So we just want to plug these x values into the original function. Everyone's good with the table, the first 2 rows? Now to get the third row, what we did was we combined these 2 pieces of information vertically, right? So you need to go down the frown, which means you're on which side of it? Right side. So the original function should look like the right side of a frown here. Then it should look like the left side of this smile. And then it should look like right side of the smile. and then finally left side of the frown. So those are the 4 pieces that I'm going to need to paste together to get my final picture. But now what I'm going to do is incorporate all the information I have. So I'm going to come down here. Here's my y-axis is at 0. My x-axis, I'll just put it across like this. I'll bring these straight down. 0's here, and then negative root 3. And let's start going back to the beginning. What was the first piece of information that I had determined? First thing, domain, right? So we know this picture is going to be drawn everywhere. I have an x-intercept was the next thing, and y-intercept both turned out to be this point. So I'll use a different color for my actual graph. So I have definitely a point right here, right? That point lives on my graph. What do we do after the intercepts? Symmetry. So I know it's going to be, whatever I draw over here is going to be exactly the same as over here, like reflected. And then horizontal asymptote? 1, right? So I need to go up 1. But see, I should probably get a better idea of like how high I need to go up. So take a look at the points we had. We had some points. We had 0, 0, right? That was our local min. Min? No, local min. I keep forgetting. And then at negative root 3 and positive root 3, we were up at 1/4. So it looks like the highest value I'm going to need to look at is 1, because that's where my horizontal asymptote is, right? So how about I do this? When I draw this, I'm going to put a 1 here. And I'm going to draw a horizontal asymptote. Notice I'm drawing it out towards the edges, not all the way across. Got my x-intercept, y-intercept. I had no vertical asymptotes. I have a horizontal asymptote. There it is. Then I started getting my max-min stuff, right? So I have this point. Another point I have for my inflection was at negative root 3, 1/4. Would you all agree somewhere around there? If that's 1, then that's half. That's a 1/4. Good enough? And then over here, this one. And that's it. That's everything I have, isn't it? Not missing any other pieces? So I need to draw this. To the left of this, right? To the left of this, it must look like this. So it's going to come up like this, but it has to go towards my horizontal asymptote. So I'm going to make it look like the right side of a frown. It's going to frown up to my horizontal like that. And then between these 2 points, I need to connect them with the piece that looks like this. So it must always look like the left side of a smile. Whoa, okay, I think I did okay. Darn it, good enough. I don't want it to drop below there. It's actually going to touch right there.
Does it need to be?
It doesn't have to be perfect. Just don't make this like come down and come back up or something.
Like it doesn't, right?
Yeah. Then from here to here, it's got to look like this. So and then out the right side, it's got to look like this and flatten out towards that. So again, does that look like an even function? Yes? Symmetric to the y-axis. Do you have a local minimum here? Yes. Do you have inflection points here and here? Yes. There it is. Yes. I don't know. Because it looks like a bat.
You never seen like the Batman symbols?
I think we have some disagreement there. You like Batman, right? Yeah, that's, I remember you mentioned that. Weren't y'all talking about comic? Weren't y'all two talking about that? Something. Like the old Batman or the new Batman? Weren't we talking about that?
Yeah.
All right. Well, that wasn't bad. It only took us about 45 minutes.
A little bit more than a typical but less than paying your taxes. Something harder.
I'm looking.
Because the last several examples have been just awesome.
You know, I mean, like every one of these problems is so unique. So every one of these problems is so unique. They present their own issues that I'm not going to be able to give you a problem just like the ones you're having for take home. All right? I would have to do that problem. Or just like change a number from a 5 to a 7 or something like that. I don't want to do that. I want you to enjoy these and suffer appropriately.
There you go. Suffer, that's a better.
Yeah. When I used to do triathlons back before I got married, we used to have this terminology that you have to pay into the suffering bank as you're training. Anyone who's done athletic stuff, you have to pay into the suffering bank. That's what the training is. You have to suffer, and then when you're actually in competition, is when you can withdraw from that bank. It pays off. But if you never suffered and paid appropriately into the suffering bank, then when you're sitting there and you're going through your competition, you're falling, you can't withdraw anything. Get that edge. I don't know if that makes sense.
It does.
We all have to suffer through this, so.
I used to do a marathon, so it makes sense.
Yeah, in anything. You could associate that to anything. So I don't mean that in a mean way, like you have to suffer. I want you all to suffer. All right, well, here, let's do this one. This is pretty close. This is pretty close to one that you have. So I'm almost kind of giving you a lot here, all right? There's some subtle differences, but very subtle. First step, domain. It's not all real numbers, right? You can't take the square root of a negative number. So automatically we have some things that are thrown out here. So what we do in a standard problem like this is we look at the radicand, the thing underneath here, and we ask ourselves, what would be okay? As long as that's bigger than or equal to 0, right? As long as what's under there is not negative, which is the same as saying greater than or equal to 0, then we're good. So now this is called a linear inequality. All we do is add x to both sides. And this is telling us that the x values that we plug in must be smaller than or equal to 5. Understand? And if you look at that on a number line, here's 5. Smaller than or equal to 5 means stuff this way, doesn't it? To the left? Including 5 itself. 5 can be plugged in, right? Because you can take the square root of 5 minus 5 is 0. You can take the square root of 0, that's 0. So 5's okay. So my domain, written out in interval notation, is negative infinity to 5 with a bracket. That's the domain of the function. Everyone understand the logic behind all that? All right, next thing. X-intercept. X-intercept. I want to sing L'Hopital, but there's no reason to sing L'Hopital. X-intercept, I set the function to 0, right? Set the function to 0. So if I set the function equal to 0, because this is multiplication right there, I can set each of those factors to 0. So I set x equal to 0, and I set 5 minus x equal to 0. Or root. But I can square both sides, can't I, on that root? So what are my solutions? I have x is 0 is one answer. And then over here, 5 minus x is 0 when I square both sides, so x is 5. I have two x-intercepts. Are both of these in the domain?
Yes.
Yes, they're in here, right? Okay. How about y-intercept? Plug 0 into the function, right? So what do you get if you plug in 0? You get 0. And it turns out that your y-intercept is actually corresponding to the x-intercept of x is 0. Won't that always happen? If you have an x-intercept that's x is 0, isn't that always going to be your y-intercept too? Mm-hmm. Yeah. So it's not a coincidence. Well, what's next? Symmetry. Well, I can throw out all ideas of symmetry. And the reason why is because I don't even have a symmetric domain, right? My picture is only going to exist to the left of 5. So it's impossible for me to say this is a reflection over unless it went between -5 and 5. Then it could be reflected. Understand? But it would be impossible to be a reflection. Do y'all get what I'm saying or not? Like if this goes on like this, then you couldn't reflect it over here because it would be cut off. So symmetry is out the door. But you could check it. I mean, you could check to see, but not going to. You don't need to check. No.
You have to explain what there is.
Yeah, symmetry, none. Because intervals, because your domain is restricted, right? Fourth step, asymptotes, right? Fourth step, horizontal asymptotes. Wait, no, vertical. Let's do vertical first. Vertical, do we have any vertical asymptotes?
Well, it can't be past 5.
Do you ever get division by 0 though? No. So none? No verticals? All right. How about horizontals? Two limits, right? Limit x goes to infinity of the function, and the other one, limit as x goes to negative infinity of the function. What can you tell me about that first limit? What's that?
Yeah.
The root of, I agree it's infinity times root of negative infinity. That's a problem.
Yeah.
It's imaginary. But wait a minute. Why are we trying to figure out what happens as x goes to infinity if our domain stops at 5?
That was a trick question.
Right?
How do you do this?
I was just asking you what the limit was. Right? Domain. We don't need to look at that, right? We can't go past 5. So why let it go to infinity? Now can we go the other way?
Yeah.
You can go the other way though. Right? You can go to negative infinity?
Well, it's only infinity.
Yeah, let's see what happens. If you let x approach negative infinity, this right here is negative infinity, right? Times the square root of 5 minus negative infinity. Get the idea? Minus a negative would become plus. So this is 5 plus infinity. 5 plus infinity is infinity. Square root of infinity? Infinity. Infinity times negative infinity. Negative infinity. That one's okay. So this is turning into negative infinity times infinity, which is negative infinity. That means when I draw this and I start going to the left, this thing is going to take off this way, down. Right? So it doesn't have a horizontal asymptote in the sense that it's not going to flatten out to something. But it is going to head out. As I go to the left, it's going to head down. With me? All right.